I am Dr. D.K. Tripathi, Assistant Professor of Physics under the Department of Basic Science and Humanities. Today, we will discuss about the applications of Fermi-Dirac statistics. So, first application which we will discuss, that will be the application of Fermi-Dirac distribution law to the metals or conductors. What happens in the metals? In the metals, very large number of electrons are present which are free to move from one part of the conductor or metal to the other part. Now, when these electrons are moving from one part of the conductor to the other part, they are carrying the energy and they are colliding with the other electrons in their way. Not only that, they are colliding with the fixed positive ions in their way, and also they collide with the skin of the conductor. Now just think about the gaseous enclosure in which gaseous molecules are there. At what happens? That gaseous molecules are moving from one place to the other place. When they are moving from one place to the other place, they are colliding with the other gaseous molecules. Those gaseous molecules which are still or are moving, they collide with both of them. These gaseous molecules also collide with the walls of the container. So, what we can say that the gaseous molecules are resembling the electrons in the conductors. As gaseous molecules are free to move from one place to the other place, like that electrons are free to move from one place to the other place. As gaseous molecules are colliding with the other gaseous molecules as well as the walls of the container, like that the electrons are colliding with the fixed positive ions, they are colliding with the electrons, and also they collide with the skin of the conductor. So can we say that the electrons resembles the gaseous molecules and conductor or metal resembles the gaseous enclosure, and hence the conductor or metal should be called as the electron gas, which is made of electron particles. Now we will have to apply the Fermi-Dirac distribution function to know the Fermi energy. So at first our task will be to find out the number of electrons. Now let us suppose a conductor in which a very large number of free electrons, as seen in the diagram, very large number of electrons are there. So what we can say, that conductor is an ensemble of large number of electrons. Now in the first class I told you that all these electrons will not have the same energy. So those electrons which will have the energy equal to even energy level, they will be placed in even energy level. Those electrons whose energies are equal to the energy of the E2 level, they will be placed in E2 level, and like that those electrons which are having the energy equal to the nth energy level, they will be placed in nth energy level. But what we know, that electrons are never put in the energy levels directly, rather than that they are put in the energy states. So if we take that E1 energy level is having G1 number of energy states in which N1 number of particles are filled. E2 energy level is having G2 number of energy states in which N2 number of particles are filled. Like that, if we take an energy level as the test energy level, suppose energy level EI. So this energy level EI is if having Gi number of energy states in which Ni number of particles are filled, and like that if we take that nth energy level is having Gn number of energy states in which n number of particles are filled, then our aim is at first to find out the total number of electrons in the ith energy level or test energy level. When we will be able to find out the total number of particles in the ith energy level, we will integrate it to get the total number of electrons in the whole ensemble or whole conductor. Then when we will be able to find out the total number of electrons, then we will be able to find out the total energy of the. As discussed in the last slide, that a very large number of electrons are available in the electron gas. Now, if very large number of electrons are available, then the energy levels which are shown as discrete in the last slide, that will not be discrete. Rather than that, the energy levels will overlap to each other. That means due to the ability of very large number of electrons, the energy levels becomes continuous rather than the discrete one. So there we will not be able to designate the levels as E1, E2, E2, E3, E4 like that. And if we will not be able to designate the discrete energy levels, then it will be somewhat typical to apply the Fermi-Dirac distribution function. Then what we will do? We will try to find the total number of electrons in an energy range. Suppose the energy range between E and E plus dE, where d is very small range. So we will try to find out at first the number of electrons in the energy range E and E plus dE. For that, if we suppose that there are total GeDE number of energy states or quantum states in which NeDE number of electrons are filled in the energy range E and E plus dE, then Ni equal to Gi, which was at T equal to 0 Kelvin when test level energy is less than the energy of the Fermi level, will change to NeDE will be equal to GeDE, because we don't have any other way. So what we will try to find out? We will try to find out that what is the total number of electrons at 0 Kelvin in the energy range E and E plus dE when the reference energy level is greater than the energy of the test level. So that is why these are changing, NeD equal to GeD. Now here we will have to know a very important concept which is called as density of states. Earlier this was in the syllabus and this was to discuss in detail. Not only that, the formula was also to be derived, but now this is not in the syllabus, so we will use it. That is why we will just try to have the idea of this. For that, density of state is what? Density of state is the number of microstates in a per unit energy range. That means if you are taking the energy range E and E plus dE, so in that very energy range, what number of microstates are available? That is called as density of states. The definition of density of state is the number of microstates per unit energy range. If dE is equal to 1, because we have considered the energy range as E and E plus dE, so what will be the range? Range will be dE. If dE equal to 1, then what number of energy states are there or what number of quantum cells are there to fill the electrons in unit energy range is called as density of state. So density of state is defined as the number of microstates per unit energy range, and it is given by GeDE is equal to 8 pi mv 3 GeDE is equal to 8 pi v m 3 by 2 E half by h cube, where h is Planck's constant and E is the energy, m is mass of the electron, v is the volume, and 8 and pi are there, what are constant. So in the last slide we have seen that GeD equal to 8 pi v m 3 by 2 E half by h cube. Now at T equal to 0 Kelvin, when EI is less than EF, we have seen that Ni equal to Gi. Because of that, NeD will equal to GD. So the value of GD will be equal to NADE. Because of that, we will get NADE will be equal to 8 pi V m3 by 2 E half by h cube. Now this is the number of electrons in the energy range E and E plus DE. So the total number of electrons in the whole ensemble, that will be the integral of this relation. So if we integrate both sides, what we will get, capital N, which is the total number of electrons considered in the whole ensemble, will be equal to the integral of NEDE, that will be equal to 8 pi V m3 by 2 E half dE by h cube. Now you see, 8 pi V volume will be constant. Why? Because you are taking the constant volume, mass of the electron is constant, and h cube, the value of h, Planck's constant, is also constant. So all these terms will come outside. In the outside of the integral, we will get 8 pi V m 3 by 2 by h cube, and E half will be integrated with respect to dE, and due to that we will see the result in the next. So when we will integrate E half within the limit 0 to EF. Now one thing to be known here, that why we are taking the limit 0 to EF, because you have seen that at absolute zero temperature all the levels right from the ground state up to Fermi level are filled, and above that there is no particle. So here also the electrons will be filled up to the Fermi level. So that is why the lowest limit will be 0 and highest limit will be EF, that is Fermi level. So this will give us EF 3 by 2 by 3 by 2, which in turn gives us 16 pi V m 3 by 2 E f to the power 3 by 2 by 3h cube, which is the total number of electrons in an electron gas. This is always asked in 4 marks to derive the total number of electrons in the electron gas, or total number of electrons in metal or in a conductor. So this is very important relation which we have got, that gives us the total number of electrons in the whole ensemble. Now from that you can see that a Fermi level, the value of Fermi energy can be found out. For that, EF will be equal to h square by 8m 3n by pi V to the power 2 by 3. That will be the value of the Fermi energy in the electron gas or metal or semiconductor. Total energy of electron gas at absolute zero temperature. Total energy of electron gas at absolute zero temperature can be found by multiplying the energy of one electron with the total number of electrons. So if we suppose E naught total as the total energy at absolute zero, capital E as the energy of one electron, and N is the number of total electrons in the whole electron gas, then E naught total is equal to E into capital N. Now capital N is what? 0 to EF NED. So you replace this N by 0 to EF NED, and at 0 Kelvin temperature we have seen that NED is equal to GED. That means what number of electrons are available, that number of quantum cells are available. So due to that we will put the value of GED. We have discussed in the last that what is the value of GED, that means number of quantum cells per unit energy range. So the final expression will be equal to 0 to EF 8 pi V m 3 by 2 E half dE by h cube into E. Now we will take out the constants outside, and within the integration integral there will be 0 to EF E 3 by 2 dE. This will give us 16 pi V m 3 by 2 EF 5 by 2 by 5h cube. Now n was equal to 16 by 3, pi v m 3 by 2, ef 3 by 2 by 3h cube. So this expression will be equal to 3 by 5 NeF. That means we can say that the total energy of the electron gas is equal to 35 n times the Fermi energy. Average energy of an electron at absolute zero or 0 Kelvin. Average energy of an electron is what? Or average kinetic energy of an electron at absolute zero. This will be equal to the total energy by total number of electrons. So total number of electrons is capital N, and total energy we have just calculated in the last slide, that was equal to 3 by 5 NeF. So here E average will be equal to 3 by 5 NeF by N. N and N will cancel each other, and because of that we will get 3 by 5 into EF. What does this mean? This means that average energy per electron at absolute zero is 3 by 5 times the Fermi energy of the electron. Now next is Fermi temperature. What is Fermi temperature? Fermi temperature is the temperature corresponding to the Fermi energy. If we take Tf as the Fermi temperature, Ef is the Fermi energy, and K is Boltzmann constant, then Tf will be equal to Ef by K. These are some of the references which you must pursue to know more about the topics. Thank you.